Welcome everyone, and it's great to have you from attending this session that Dr. Alexandra Mueller will be providing. I am Professor Mark Stevenson. I'm a Director of the Transport Research Lab at the University of Melbourne, and I'm delighted to work with Alex today, wherever you're listening from, on what we're going to have a fascinating session on potential safety impacts of crash avoidance systems, driving automation, and autonomous vehicles. So very much a focus on 21st century transport safety. And before Alex starts, I'm just going to give a very brief introduction to Alexandra Mueller. So Alexandra is a research scientist at the Insurance Institute for Highway Safety, which is a renowned research institute in the US. And Dr. Mueller specializes in human factors research with a focus on advanced driver assistance systems and driving automation. She received her bachelor's and master's degrees from the University of Guelph and her doctorate from the University of Western Ontario in Canada. Dr. Mueller completed postdoctoral fellowships at McMaster University and the Cincinnati Children's Hospital Medical Center. So welcome, Alex, and we've got tonight, you're going to give us 3 presentations of about 10-15 minutes, and probably the format's different in terms of our coursing meeting, then that we're going to have questions for you after each of those 10-15 minute presentations. So I encourage all those who are attending this session to send through on the chat session questions to me, so that we can post those and I can pass them on to Alex at the end of her session, and we'll have a discussion of those for about 5 to 10 minutes, and then we'll move to the next presentation. So thanks everyone for joining us, and we're looking forward to having a very interactive session, and over to you, Alex.
All right, well, thank you very much, Mark. So for this session, I'm going to talk about the safety benefits and risks associated with different types of vehicle technologies. Throughout the session, I will, let me see if I can get this, there we go. I will refer to vehicle technologies on an automation spectrum using the SAE International definitions for levels of driving automation. I'll show you a figure to explain what those levels are in a minute. But as Mark said, this presentation will be separated into 3 different parts. The first 2 parts will cover technologies that are available in vehicles today that you can buy. The first part of the session will cover crash avoidance features, and the second part will cover more sophisticated level 2 systems. On the topic of level 2 systems, I will discuss their impact on traffic safety and how the human element needs to be better accounted for in their designs. And finally, the third part of the session will discuss autonomous vehicles. Autonomous vehicles or self-driving vehicles are not available to consumers today, but there has been a lot of speculation about what their impact will be on traffic safety. And I'm going to talk about those expectations and why they might be premature and why we should not take their potential safety benefits for granted. So let's quickly cover what the distinctions are between the levels of driving automation. I'll go into more detail for the different levels in their respective parts for this session. But for now, I want you to pay attention to how the driver's responsibility and roles change between the different levels. Most crash avoidance systems are not considered to be a form of driving automation, and so they are called level 0 systems. And the levels go from 0 to 5. Some systems can apply the brakes like forward auto brake or steer the vehicle temporarily like lane departure, but that type of active driver assistance is merely temporary, and the driver has full responsibility of the vehicle at all times. The vehicle is considered to have driving automation assistance or adaptive, that's like adaptive cruise control, or have partial automation, such as combined adaptive cruise control and lane centering, when it supports the driving task for extended periods. But for both the level 1 and 2 systems, again, the driver is fully responsible for the vehicle at all times. The higher levels of automation that I'll talk to you about in the third part of the session concern levels 4 and 5. And those systems are considered to be self-driving where no driver is required. But the difference between levels 4 and 5 is the fact that level 4 has restrictions on when and where the driving automation can operate, whereas level 5 does not. And now it's important to emphasize here that the levels of automation as defined by SAE only apply to production vehicles. This means that vehicle test programs that you hear about in the media, for example, with respect to Uber or Waymo, do not fall under these definitions because those programs involve prototypes and pre-production systems. So let's get started and talk about crash avoidance systems. Crash avoidance systems generally fall into two different types of categories. There are systems that simply give alerts to the driver, for example, when another vehicle is in the driver's blind spot or when the vehicle drifts over the lane line. Other systems temporarily act on behalf of the driver to avoid an imminent collision. Examples of those systems include, for example, forward auto brake, when the vehicle automatically applies the brakes when there's a risk of rear-ending a vehicle in front of you. Or for example, lane departure prevention, where the vehicle automatically nudges itself back into the lane when it detects an unsignaled lane departure. And as I mentioned earlier, the SAE levels have been developed categories of driving automation. And as I said, crash avoidance systems are considered to not have any driving automation. In other words, they're level 0. And this is because, again, they're transient alerts designed to get the driver to respond, or they offer only temporary intervention when the driver has failed to respond appropriately. And I have good news. We are seeing that crash avoidance systems really are living up to their expectations in terms of preventing the types of crashes that they were designed to prevent. When I say preventing the types of crashes they were designed to prevent, I mean, for example, forward auto brake systems preventing rear end crashes, or lane departure prevention systems preventing single vehicle head-on or sideswipe crashes, or even blind spot detection preventing lane change crashes. And then we are seeing that these systems both alert and intervene on behalf of the driver. Those ones are the most effective in preventing crashes as compared to the systems that just give alerts to the driver. For example, combined forward collision warning and auto brake systems help to prevent approximately 50% of police reported rear end crashes, which is much higher than just forward collision warning on its own. And the safety benefits of these technologies have led to the Insurance Institute for Highway Safety's 3 crash prevention testing programs to evaluate front crash prevention systems, rear crash prevention systems, and most recently, pedestrian crash prevention systems. And as you can see, our crash avoidance system ratings are demonstrating yearly improvement in these systems from different manufacturers. But we are still seeing variability in the efficacy of auto brake systems between makes and models. Some of those systems can detect both vehicles and pedestrians. This is an example of the forward crash avoidance system detecting and braking for pedestrian dummy for tasks. But as you can see in this photo, other systems do struggle to detect and respond to pedestrians. And so what this means is that despite the benefits that we are seeing in the crash avoidance systems, there is absolutely a need for further development and refinement. Not all crashes are the same type, such as rear end crashes. They don't involve the same situations all the time. So look at this example of a rear end crash in a very uncommon rear end crash scenario. So this vehicle very likely did not have any crash avoidance systems, but even if it had, it's very unlikely that forward auto brake would have been able to prevent this type of crash. And even though we are seeing that these systems do have measurable benefits for typical crash scenarios, their benefits do diminish for less typical scenarios. And despite the growing popularity of these features, they are still fairly uncommon in the registered vehicle fleet. This graph shows the new vehicle series with front crash prevention systems in the United States offered by automakers every year. And you can see that more vehicle series are being offered with these systems as standard or optional every year. And this graph is just representative of the new vehicle series available in the United States. But as you can see on this slide, very few vehicles on the road actually have these features. And it's important to consider the slow uptake when thinking about expectations that people have for more sophisticated forms of driver assistance technologies and even autonomous vehicles. Those technologies are and will be even slower to penetrate the fleet. And so the expectations that you might have heard about their potential safety benefits really do need to be considered with caution, considering first and foremost how long it takes, and second, the number of equipped vehicles on the road that are necessary to collect enough data to objectively evaluate the safety benefits of vehicle technologies. Nevertheless, the lag in uptake gives automakers the opportunity now to improve the capabilities of driver assistance systems as they begin to proliferate the fleet. So I think we can take a break now and for any questions.
That's terrific, Alex. I mean, just comes to mind just thinking about, I know the average fleet of the age of the fleet in Australia is about 8 years. And so I was just trying to realize what the potential, the population health, public health potential in terms of reduced trauma would be in terms of those sorts of safety devices, you know, reaching into the fleet. And it's unlikely we're going to see that for many, many years, isn't it?
Well, I mean, we are seeing, if you're talking about the more basic crash avoidance systems, we are definitely seeing a benefit. For example, and there has been a concerted effort across the industry to make these systems more widely available. For example, in 2022, there is an agreement to, among most manufacturers, I believe it's like 99% of the North American automobile fleet, to have forward auto brake equipped in vehicles on offer in new vehicles. And of course, that's going to have hopefully tremendous benefits in terms of public health. But another consideration that's important to bear in mind is that that also will increase the price of, for example, repair. And that's an ongoing concern. So the hope is, as these systems become more standard, that will start evening out the cost benefit as well.
Yeah, I know.
Raising the benefit relative to the cost.
Yeah, I guess I'm just thinking about, I know in Australia ways to try and facilitate that uptake, and I know some of the discussions have been held around the potential to ensure that government fleets all have many of these features like autonomous emergency braking fitted, because they stay, you know, the fleets are generally held for approximately 3 years, and then they become, you know, they're out of the public market, and therefore they can saturate the market quite readily if there's thousands of vehicles purchased. I mean, are those, has, you know, your institute looked at those sorts of strategies to try and almost accelerate the potential uptake of?
Mark and Alex, this is Kavi. We have a request from the interpreter. So there's live translation happening in Spanish, and they're finding Alex speaking a bit too fast for them to keep up. Alex, could you just speak a little slower?
Sure.
Great. Yeah. Do you want me to repeat that at all, Alex, or you?
No, basically, I understand the concerns that, like for rapid uptake, but the thing is, we know that vehicle turnover in the consumer fleet is quite long. The last estimate I heard was around a decade, approximately. And when you think about the life cycle of these technologies, and you know, the fact that these systems are fairly new, and of course, the more sophisticated systems available, not only are they fairly new, but they're also much more expensive. So in terms of their ability to penetrate the fleet, those are significant barriers to overcome: vehicle turnover, cost, and those are just barriers that, frankly, I don't think there are necessarily public funds to start, you know, subsidizing and encouraging consumers on their own to adopt and to purchase brand new vehicles, because these will generally have to be brand new vehicles.
Yeah.
And that doesn't even address the used market.
Yeah. So Alex, we have two questions that have been posed as well. One is from one of the questions, I'm not sure if it's from Dinesh or who it's from, but it says, one of the main reasons pedestrians wait patiently at the side of the road for a car to pass before crossing the road is because they would die if the car didn't stop. In a world where all cars have automatic braking, wouldn't pedestrians just wander across streets everywhere and all of the time? Should we expect a resurgence of jaywalking laws to keep pedestrians off the streets in a world with automatic braking?
Well, I mean, we have automated braking in vehicles now, and we have pedestrians having terrible jaywalking related crashes, and even crashes with pedestrians at intersections where pedestrians are, obeying the laws and crossing at designated crosswalks. The fact is, automated braking is a driver assistance system, but it will never, it's completely unethical to expect it to operate perfectly for every single circumstance. As I mentioned before with that video where a vehicle was crossing multiple lanes on an interstate, there are certain scenarios and certain angles that these systems cannot respond in time to avoid a crash, or even detect that a crash is imminent, because of angles or the appearance of the hazard are just not recognizable by the vehicle system.
Yeah.
So the fact is, these systems, although they're having measurable benefits in terms of reducing the types of crashes for which they were designed to prevent, it's unreasonable to expect them to be 100% perfect every single time. And of course, it's impossible for the pedestrian to know which vehicles are equipped with forward auto brake and which ones are not. And as we just talked about with vehicle turnover, it'll take a long time before even most vehicles are equipped with forward auto brake. So this utopia of pedestrians be able to walk wherever they want, whenever they want, is just not reasonable. I mean, a car is always going to win against a human being.
Well, I guess, and your human factors background is very valuable here, in that there's obviously the human factor component of this transition. And clearly pedestrians are not going to be, forewarned as to what a vehicle, has in terms of safety features. But I guess the point, having just purchased recently a new car, that's the first car I've had with autonomous emergency braking, there are significant skill sets that as a driver that you need to be made aware of with these new features as well. And I can see the potential for many new drivers, particularly older drivers, of wishing to switch these features off. And I guess that's an important component of the evaluation of the effectiveness of such as well. And I guess you're coming up against that all the time.
Well, I'm actually, Ian Reagan at the Institute did a study on that, looking at the actual usage rates. And certainly some systems are more widely used than others. Even if all the systems are equipped on the vehicle, the driver may not necessarily use those systems. Some systems are perceived to be very annoying by the driver based on their alerts and the method of alerting. Drivers tend to find haptic alerts and visual alerts more appealing than audible alerts. Audible alerts are very irritating, and there's also a social component with that too, of if you have a passenger in the vehicle with you and you have an audible alert going off and nothing is actually happening. Let's say it's a false alarm, or let's say the driver was proactively responding when the alert happened, or intentionally doing a behavior that actually caused that alert. Like, for example, if you straddled the lane line to give another vehicle more room, and you have the lane departure warning go off. And if it's an audible alert, there's a social component where the drivers actually perceive embarrassment because it seems like they're doing something wrong, and that's what the visual alert is kind of communicating. And that's why, for example, seat haptic and visual alerts are more well-liked among drivers. And of course, that influences likelihood of use. And one thing that you're going to see repeated throughout this presentation is that just because you have the systems available in your vehicle is not a guarantee of their efficacy. People have to be using these systems for these systems to actually work. These systems.
Yeah. Well, I mean, I just experienced the autonomous emergency braking was actually a shock for the first time.
Oh yeah, it's
Typical
aggressive.
driving, it's very aggressive, and
It's very
typical
aggressive.
driving where I might be at an intersection waiting to turn, and an oncoming vehicle is coming close to my vehicle. It slammed on the brakes, and it was my wife was sufficient to say, we should need to turn that off. That's frightening, So we have challenges, and I think many of them are, as you're going to allude to tonight or today, are some of the human factor elements associated with the autonomous nature of the vehicle fleets that we're seeing.
Yeah.
The other, just before we move to the next session, is really just to also there's much attention given to the automobile by the automakers, the four-wheeled automobile rather than say the motorcycle, and yet vast majority of countries near where I live are motorizing rapidly, but they're motorizing with two-wheeled vehicles.
Mm-hmm.
I'm aware that there is autonomous emergency braking now on motorcycles, but do you have any insights in relation to just what sort of impact we're likely to see from some of these features on motorcycles?
That I don't know. I don't. I would expect the patterns probably to be a little bit different. It's again, motorcycles have certain considerations that four-wheel vehicles don't. They have maneuverability that four-wheel vehicles do not. They are able to weave in and out and perform certain movements that four-wheel vehicles are not capable of. And they're also much smaller than four-wheel vehicles, which also has a problem for other vehicles. Like let's say a four-wheel vehicle is equipped with automated emergency braking. It's not guaranteed that that system will recognize the motorcycle, both because of its speed and its size. And so whether the motorcycle's autonomous emergency brake or automated emergency braking system will have the same effects as four-wheel. I mean, there are also physics to be considered as well with a two-wheeled vehicle versus a four, in terms of how also that abrupt braking that you experience. Remember, the very aggressive braking that you experienced could potentially have serious effects on a motorcycle at speed. So, and that could actually hypothetically even make a crash situation worse with abrupt braking. So I would imagine that these systems have to be developed differently as well. So it's not, to my knowledge, it's not clear what the actual safety benefits look like for motorcycles versus four-wheeled vehicles.
Look, that's terrific, Alex. If you want to continue, we've got no questions in the chat and the Q&A. So
All right.
If you'd like to move us through to the next presentation, that'd be great.
Sure. So we've talked about basic crash avoidance features that are available in vehicles today, but there are more sophisticated vehicle technologies out there as well. And so I'm going to talk to you right now about partial driving automation, or what is also known as level 2 systems. So remember how I showed you this slide at the beginning about the different levels of automation. Remember, level 1 has the vehicle support the driver in one aspect of the driving task for an extended period. But again, this is not a self-driving vehicle. The driver has to be involved in the driving task at all times. And adaptive cruise control falls under this level 1 category. Level 2 driving automation provides sustained support to multiple aspects of the driving task through adaptive cruise control and lane centering simultaneously. And again, that's sustained support over extended periods. But however, just like level 1, level 2 driving automation is not autonomous. And again, that means that the driver still has full responsibility for the vehicle's behavior at all times. In fact, one thing that's interesting about level 2 driving automation is that it actually changes the nature of the driving task. This type of driving automation is designed to make the driving task easier by removing some of the physical workload in vehicle control for multiple aspects of the driving task. Specifically, a level 2 system helps control the vehicle's speed, distance to vehicles ahead, as well as help keep the vehicle centered in the lane. But an unintended consequence of this type of driver assistance is that partial driving automation can actually make the driving task harder. This is because the driver has to take on a new supervisory role by constantly monitoring both what the vehicle is doing and what's happening in terms of that vehicle's performance in the road environment, just in case that vehicle encounters conditions it is unable to handle. And we'll talk about what those conditions are in just a moment. But it's also worth noting here that it's not clear, and it remains to be demonstrated whether level 2 systems have true safety benefits in terms of crash avoidance above and beyond the more basic crash avoidance systems. And so the problem with level 2 systems requiring the driver to assume a supervisory role is that it becomes very difficult for drivers to maintain the necessary attention needed to supervise the vehicle and the road for extended periods when much of the normal physical workload is removed. There is also the risk that the driver could begin to overtrust the level 2 system to be more autonomously capable than it really is. Overtrust carries the risk that a driver could give over more responsibility to the vehicle to drive itself and for it to handle more traffic and road conditions than it was designed to. And as you might expect, this comes at the risk for drivers becoming distracted and doing things that they really should not do because these systems are in no way self-driving. And so level 2 systems are not self-driving, yes, but this raises the question, why is reduced driving engagement or driver engagement dangerous when using these systems? And the reason for this is these systems often behave in ways very suddenly that are unexpected to the driver, which is why the driver needs to stay engaged in the driving task to take over at a moment's notice. In this video, you can see examples of how adaptive cruise control is limited in how it responds to stop vehicles ahead. You can see in this video that many of the systems gave a forward collision warning alert without adaptive cruise control actually slowing down the vehicle. In each instance, the driver had to take over by applying the brakes to avoid a crash. And what this video highlights is that some hazards on the road can go completely undetected by level 2 systems because of the shape or angle of objects and where they're located on the road, meaning that the vehicle is unable to recognize them and perform the necessary avoidance maneuvers. And this is again what we were talking about before with the auto brake systems not necessarily being able to recognize all different kinds of, for example, pedestrians or vehicles on the road, even once they become more common. And systems from different manufacturers also vary in how they behave when they encounter challenging driving conditions, such as curves or hills. Some of these systems are more successful than others at keeping the driver within the lane, but that ability seems to vary for different road conditions. Our on-road functional testing of these systems has shown that there is actually quite a bit of performance variability across different road conditions for different manufacturers. Some vehicles particularly struggle with hills, whereas others struggle more with curves. And the reason for this variability and why curves and hills are so challenging for these systems is because these systems rely on forward-mounted cameras and radar. And that means that line of sight for these systems is necessary to maintain alignment with the road. And in these videos, when you see the vehicle drift over the lane line, the driver actually had to take over and steer the vehicle back into the lane. Hills, as you can see, also pose a challenge for the forward-mounted cameras because the angle will be pointing upwards away from the road when moving along an incline. And as you can see that when the vehicle drifted over the lane lines, the driver once again had to take over and bring the vehicle back into the lane line, or back into the lane. And in this last video, you can see, again, the variability. This vehicle was able to keep itself centered as it went over the hill. And The problem, as I mentioned before, with respect to drivers becoming disengaged from the driving task when using these systems is that we are seeing real world consequences for people misusing these systems. Many of you have probably heard about the high profile NTSB crash investigations concerning Tesla's level 2 system called autopilot. Tesla's autopilot monitors the driver in terms of having his or her hands on the wheel as a way of determining if the driver is engaged in the driving task. And unfortunately, leading up to these crashes, the drivers had their hands off the wheel for prolonged periods. And this indicates that the drivers were not paying attention when the system behaved in ways that were unexpected. And because they were not engaged in the driving task, they were unable to intervene before it was too late. And in some of these crashes, autopilot struggled to distinguish the lane markings, the road seams, and the gore area when the roadways split. The growing area of the gore at the split was misinterpreted as a third lane in which the system tried to center itself. And again, due to the fact that the drivers in these crashes were not attending to the road and monitoring what autopilot was doing, the vehicle crashes, or the vehicles ended up crashing in the crash attenuator and barriers. And this is a photo showing an example of one of the crash scenes where autopilot struggled to distinguish the lane from the gore area. And I'm going to show you a video demonstrating how the system struggled with the lane markings and road design. And one thing that's important to note about this type of scenario is that it's not uncommon, and limited access roadways such as interstates and highways are the types of road conditions for which these systems were designed to operate in. And before I conclude this portion of the session, I would just like to highlight that crash avoidance systems remain important for level 2 systems in their emergency responses. For example, forward auto brake has a much stronger capability than adaptive cruise control, and as a result has significantly shorter stopping times. Lateral collision prevention systems also assist when making lane changes, for example. Remember, these systems are not in any way self-driving, and the driver does have to be in a supervisory control state when even making lane changes. And so again, these systems do help to enhance the driver's situational awareness of the road. And so given their continued importance, it is really imperative that level 2 systems not be operable if crash avoidance systems are turned off. All right, we can take a break now, I think.
Oh, terrific. Again, Alex, just raises so many questions for me. I sort of think it just makes me reflect on just how far we've come in terms of the vehicle itself and the safety elements within the vehicle. But if you think, you know, as you alluded to at the outset, I mean, you know, there's considerable variation, and well, human factors play quite a part in crash propensity. I guess what I'm taking from this presentation is we've sort of grappled with that for many decades, the human error component of driving. But what we're seeing here, particularly as we move from level 2 to level 3 to level 4, is an increased level of complexity. But in fact, what I'm seeing here is an increased level of variability in terms of further errors that are being introduced now by the levels of automation that are being introduced. So not only do you highlight that depending on the type of vehicle you purchase, you have levels of efficacy of the systems that are operating, the automated systems. And so you've got variation across fleets now, or across vehicle types based on capability of the engineering. And then you've got another factor, and clearly this is probably not a new factor, which is road infrastructure and crash propensity. But actually what we're seeing here is that it's not necessarily, we're not talking about sort of the hard infrastructure, we're actually talking about the softer infrastructure such as line markings, you know, are going to be playing much more integral role in crash propensity as well as we move through levels of automation. So, you know, it's becoming more complex, but in fact what it could be doing is introducing unforeseen risks and challenges that, you know, are unintended consequences. On top of the ongoing human error component, particularly in those level 2, 3 transitions in the SAE levels. I mean,
Yeah,
just your
but one
thoughts
thing
on
I think
that.
that's important to remember about that is that the levels of driving automation are not linear. They each level has their own human factors and safety considerations. And the thing about level 2 driving automation that makes it distinct from level 1 is the fact that multiple aspects of the driving task are being supported. And that takes away a lot of the physical workload from the driver, which actually physically removes the driver from the driving task. And that distancing makes it harder. I mean, this has been well demonstrated in not just the automotive industry, but it's been well demonstrated in aviation. It's been well demonstrated in robotics and military applications that human beings are not good at supervising for extended periods when they're not physically involved in a task. And they have to monitor multiple aspects of what the automation is doing. And this is a well-known issue, and part of the solution is to not only have effective driver monitoring strategies implemented with these systems, to have these systems monitor the driver, make sure that the driver is actually engaged. And of course, that means that more than one behavior has to be monitored about the driver. The more overlap you have of behaviors, the stronger the signal and the more reliable that signal will be. And so, I mean, this involves visual attention monitoring. This involves a physical connection of the driver to the driving task as well, to ensure that the driver is in fact engaged in the driving task. But not just that, there also have to be proactive driver management strategies embedded in the system design itself in terms of how the drivers actually use it. Collaborative steering, for example, has been shown to be more successful with respect to keeping drivers engaged in the driving task. So even though the driver is still receiving support from the lane centering system to remain centered in the lane, the collaborative steering approach basically requires the driver to actively still participate in the driving task. So the steering is made easier with fewer mistakes being made by the driver, but again, the driver is required to continue to be an active participant. And this just prevents the driver from checking out and falling out of the loop of the driving task. So again, these proactive strategies, in addition to effective monitoring strategies, are necessary specifically to the level 2 system that, you know, I mean, there are, of course, arguments for having driver monitoring even for level 0 systems, because we know people will be distracted behind the wheel. People will become disengaged from the driving task, regardless of whether there is driving automation in their vehicle or it's just having the driving automation available in your vehicle creates more opportunity for that distraction. It's not that distraction is unique to the level 2 driving automation. That's not what we're saying. We're saying that the automation provides more opportunity for the driver to become disengaged. And that is where those driver monitoring and management systems are so necessary.
So you could infer from that, Alex, that it could be that we see, in relation to safety, optimum levels achieved from level 2 or level 3 automation rather than right through to level 5. Could that be the case where you've got these components?
Well, the thing is, right now we don't. The data remain to demonstrate, remain to be collected to demonstrate whether level 2 systems actually have measurable safety benefits beyond the crash avoidance system. Crash avoidance systems, again, level 1 systems, level 0 systems, are showing measurable safety benefits. There is some indication that adaptive cruise control might have some safety benefits with respect to reducing opportunities in which crash avoidance systems need to activate. So they might minimize those higher risk scenarios in the first place. But again, that remains to be seen. I think Dinesh is trying to speak. I'm not sure.
Yeah, I've got a question here, but So one of the questions from the Q&A is, what is the empirical evidence, Alex, on level 2 so far? And in part, you've answered some of that. And are the Tesla crashes very rare events, and are they doing better than what is expected from level 1 and level 0?
So
2 questions here.
yeah, maybe we can break them apart.
Yeah.
The problem with the Tesla crashes is we really don't know if it's the tip of the iceberg in terms of, because remember I mentioned that level 2 systems are not very common in the registered vehicle fleet. So it remains to be demonstrated whether these systems are producing these issues with the human drivers across the population, or whether these crashes that we're seeing as investigated by NTSB, whether those ones are more representative of outlier behavior of people who are going to do extreme behaviors that may not be representative of the general population. That just remains to be demonstrated. I think regardless of which is the case, there is such a desperate need to make sure that these systems are made as foolproof as possible. Again, with the driver monitoring strategies, with the driver management strategies, that as they do start to proliferate the fleet, that regardless of whether this is an issue for the general population or more extreme outliers, these cases will nevertheless be managed or better managed and hopefully reduced. But the problem is right now there is no regulation, there's no industry-wide agreement about how level 2 driving systems should be made, should be designed. It's not clear, what sort of guidance is out there for automakers to design their systems in certain ways using the best practices. And as I'm going to talk about actually in the next presentation, it's a fine line of trying to prioritize a safety-oriented design versus a consumer convenience design, because level 2 systems, it's not really clear whether they are designed specifically for safety or for driver convenience. The operational design domain for level 2 systems are predominantly limited access roads such as interstates, highways, which have the lowest crash rates. Whereas the crash avoidance systems like forward auto brake, for example, those systems can be used predominantly in mixed driving environments such as urban, where of course crashes are very prevalent. So, and again, I mean, so I hope that answers the question about.
Yeah, look, I think that does. It does highlight what you've just. It's what I think is quite astounding. I mean, there's a lot of discussion around harmonization in terms of the automakers, but and I'm not across this as well as many others would be. I had the assumption that harmonization means in relation to the delivery of passive interventions. But maybe that isn't the case.
No, it's hugely variable. It's hugely variable, and both in terms of functional performance and in terms of driver monitoring and management strategies. And some companies are doing very well in terms of prioritizing the driver monitoring and management elements, and other systems aren't. And of course, you're also seeing variability in terms of how these systems physically perform on the roads as well. And of course, there's an interaction between the vehicle performance and the drivers being engaged in the driving task and monitoring strategies as well. So and
just
of course,
back to that question, then the last one, which was around Tesla's crashes, are they very rare events? I mean, they probably are, I guess. We tend to hear about every Tesla crash globally. I think there's so much interest in Tesla, but leave that to you to answer. And then are they doing better than what is expected at level 1 and level 0?
And as to the latter question, it's not clear as to whether they actually are doing better. Again, we need more data. And these data, there's a desperate need for more data transparency about how these systems operate, and also how they were operating up into a crash. Can access that captures both what the driver was doing, again, through the driver monitoring, what the vehicle system was doing at the time and leading up to the crash. All of these information is necessary in order to understand, really sort of the implications of what these systems are actually doing and whether they are having safety benefits, neutral effects, or even negative impacts on number of crashes occurring. And also just one thing, I mean, with respect to the lack of consistency. That's why, for example, the Insurance Institute for Highway Safety has been, we just released a series of guidelines and recommendations specifically about the driver monitoring and management strategies for level 2 systems. In that series of recommendations, we reviewed the literature and created a working document to basically capture empirically informed recommendations, because again, there's also, this is a very complicated topic in which in some cases there's no data to clearly draw a line. So we through this literature review, we made some recommendations about the different driver monitoring strategies. For example, capturing visual attention as well as the physical interactions the driver has with the vehicle while the level 2 driving automation is on, as well as driver alert methodology using multiple modalities and an escalation procedure. Also having countermeasures for when the driver is detected to be disengaged and does not respond to those attention reminders. For example, having the vehicle pulse brake, because obviously the human vestibular system is very sensitive to abrupt changes and abrupt accelerations or decelerations. So if the driver's not responding, pulse braking is a good way to send attention.
Now, I'm just mindful of our time, Alex. We can keep chatting for a long time.
No, that's fine.
We're going to run out of time, so I'm just going to finish there and ask you to start your third presentation,
sure,
so that we still have enough time at the end to have a few questions from the audience.
Okay. So switching gears, I'm going to talk to you about autonomous vehicles, or what I'm going to call AVs. There's been a lot of hype in the media about the possible safety benefits about AVs, but I'm going to explain why some of those expectations take potentially too much for granted. You'll remember how I showed you this table describing the different levels of driving automation. Just a reminder, AVs are on the far end of the spectrum. The human is no longer needed to supervise or take over when the system reaches the boundaries of its operating conditions. But don't forget the important distinction between level 4s and 5. The level 4 system, while it could be driverless, it still has limits and restrictions on where the system can operate. Most AVs, as we think of them, are, once they're in production, would be considered level 5 systems. That means that the level 5 systems are truly self-driving without restriction. And now some of you might have heard the statistic that almost 94% of crashes involve human error. This feeds into a widely held assumption that autonomous vehicles are all but guaranteed to be safer than human drivers. In particular, by removing the human element, the expectation is that AVs should reduce or even eliminate crashes once they become commonplace on the road. The problem with these assumptions is that nothing can be taken for granted when it comes to how AVs will be programmed. Maybe they will prioritize safety, as we talked about, or maybe they'll be programmed to prioritize the consumer's interest for convenience and speed. And sometimes safety can be at odds with what the consumer wants. We talked about examples with the Tesla autopilot systems, but this problem is in no way unique to AVs. Take, for example, a common technology that's available in most vehicles today, conventional cruise control. We know that speed is a major factor in crashes. If cruise control were designed with safety as a priority, it would restrict the set speed to be at or near the speed limit. But in reality, cruise control is designed more as a driver convenience feature by allowing the driver to choose any speed for the given road conditions. And right now, just as we talked about with the level 2 driving automation, there is no federal regulation or guidance or even an industry-wide agreement on how AVs should be developed or tested. And in order for AVs to truly be safer than human drivers, they will need to be programmed to prioritize safety and avoid the mistakes that humans make now. And I'm going to show you data from a study that we recently conducted that simply demonstrates how interconnected the factors that contribute to crashes are. We analyzed real-world crash data to show the general roles of AVs that they will have to perform to avoid the human-like errors that lead to crashes today. And while these findings are fairly obvious, they are necessary to help manage expectations about AVs. The data we used came from the National Motor Vehicle Crash Causation Survey, also known as the NIMVICS. Conducted by NHTSA between 2005 and 2007, the NIMVICS contains a nationally representative sample in the United States of more than 5,000 police-reported passenger vehicle crashes. Trained on-scene investigators created detailed cases of each crash with a focus on the pre-crash phase of events to identify relevant contributing factors about the parties and vehicles involved, as well as environmental, atmospheric, and roadway conditions at the time of the crash. Investigators assigned a critical reason to a single vehicle per crash that was judged to be the immediate cause for the event that made the crash inevitable. They also identified related factors that were present for every crash and wrote case summaries that described the events leading up to the crash. Now, we use those data to answer the following question. How many crashes might continue to occur in an all AV fleet if AVs are not designed to avoid the errors that humans make today? And you might ask, why did we assume 100% AV fleet scenario for this analysis? Eric Teo and David Kidd's 2017 study on the Google vehicle test program explains why we made this assumption for analysis. They found that although those vehicles had fewer police reportable crashes than human-driven vehicles per million miles traveled, they still did have crashes. Most of those crashes were from human-driven vehicles rear-ending or sideswiping the test vehicle. And so human-driven vehicles will continue to pose a threat to AVs, even if AVs are designed to be safer than humans. I would also like to point out at this point that while it's reasonable to expect a reduction in the number of crashes if AVs are designed to prioritize safety, even in a 100% fleet scenario, it is unreasonable to expect a zero collision utopia. It's very likely that the overall distribution of crashes for different risk factors will change, perhaps with more vehicle-related factors contributing to crashes, for example, with respect to hardware failures. But there will also be pedestrians and non-autonomous road users, such as cyclists, as well as road hazards, such as animals, storms, and debris. And so the point of our analysis was simply to show the diversity of driver-related decision-making errors that lead to crashes today that need to be deliberately programmed into AVs to help maximize their safety potential, or programmed to be addressed by AVs rather. And the safe operation of a vehicle can be categorized into the roles of sensing and perceiving, predicting, planning and deciding, and execution and performance. The analysis identified driver-based factors that undermine the safe implementation of these roles and led to crashes. The first four categories are related to the roles necessary to safely operate a vehicle. The fifth category included circumstances where a driver was incapacitated and therefore considered to be incapable of performing any of these roles. This slide shows you examples of the types of driver-related factors in the NIMVICS that fell into each category. Now, this is an example of a case summary for a crash in the NIMVICS database that showcases how multiple factors can contribute to a crash. I'm not going to read the whole summary, but basically the gist of it was this. The vehicle that crashed had no tread on its tires. The roads were wet from standing water from rainfall, and the driver was driving too quickly for conditions. Ultimately, what happened was that the driver's speed and tire degradation led to hydroplaning on the road and resulted in a loss of control and a crash. The critical reason cited in the NIMVIX was tire degradation. However, as you can see, human error also contributed. And so this is why we analyzed both the critical reasons and the driver-related contributing factors for every crash. And this brings us to our results. What does the distribution of crashes look like for the different driver-related factor categories? This analysis shows how many crashes had each type of factor. A crash can have more than one category of factors, which is why these blue bars tally to more than 100%. We can see that approximately 94% of crashes had at least one driver-related error, as shown in the orange bar, which is consistent with NHTSA's own analysis. Most crashes had sensing and perceiving factors, followed by planning and deciding factors, and then execution and performance factors, predicting factors, and lastly, incapacitation factors. The next step of the analysis was to investigate how the pattern of crashes would look like with certain commonly held assumptions about AVs. One commonly held assumption is that AVs should better perceive the road than humans. Crashes with sensing and perceiving factors were only considered to be preventable by AVs if they also did not have any other identified driver-related factors, as those additional factors could have contributed to the crash, even if AVs had flawless perception. Another commonly held assumption is that by removing the human element, AVs should not be vulnerable to incapacitation. Crashes with incapacitated drivers were considered to be preventable by AVs, regardless of the presence of any other driver-related factors, as it was assumed that incapacitation undermines all the driving roles that the operator must perform to safely navigate the road. The data on this slide and the next show the percentage of crashes that could persist if sensing and perceiving only errors and incapacitation no longer contributed to crashes. As you can see, 67% of crashes would still occur if AVs had superior perception and were never incapacitated, but were also not designed to avoid other types of human error. 61% of those crashes would still occur that had at least one error related to unsafe driver response.
Alex,
yes.
The interpreter is requesting to speak a little slower.
Okay. Approximately 40% of crashes were associated with intentional decision-making factors. This table shows you the distribution of crashes for common planning and deciding factors. Speeding was the most common factor, followed by illegal maneuvers, and lastly, following too closely and other aggressive driving factors. So the assumptions we tested show that only about a third of crashes could be prevented if AVs are also not designed to respond safely to what they perceive. This is far less than the 94% of crashes arising from driver error, often cited as evidence that AVs may eliminate most crashes. But I would like to emphasize that many AV developers are in fact working to address these issues. It's just that in the absence of federal regulation and guidelines, it is not guaranteed that all AVs will be designed to prioritize safety when it conflicts with what consumers want. And the way people drive today indicates that there's a collective and tacit acceptance of the risks involved with the benefits of high-speed transportation. The decision-making trade-offs that lead to crashes today, for example, with respect to the widespread tendency for speeding, indicates that AVs could be put in a similar situation unless they're explicitly programmed to avoid them. Now, AVs may not be safer than human drivers if AV designers and programmers are pressured by consumers and society, as well as businesses, to prioritize convenience and speed at the risk of undermining safety. And as we talked about, there are present-day examples of this conflict with level 2 systems that are available in production vehicles. Again, remember the crashes involving Tesla's autopilot that we discussed before. Despite the manufacturer's operational requirement for the driver to be in full control at all times, the drivers in those crashes were not being monitored appropriately to ensure that they were engaged in the driving task while using the driving automation. And I would like to point something else out that would very likely affect AV adoption when the vehicles are ultimately ready for the consumer market that we are not able to take into account into our study. That is, we do not know what other technologies will be around by the time AVs are available to consumers. It's very likely that some technologies could affect traffic safety as well as AV design and adoption in ways we just can't anticipate based on what's available right now. Look, for example, at cell phones. 20 years ago, the impact of cell phones, let alone smartphones, could have never been anticipated to have such a radical effect on traffic safety as it relates to the human vehicle interactions that we see now. The findings that I have shown you today only concern the driver-related factors that are common now and for which we have data about their effects on crashes. Our findings also underscore the importance of investing in the further development and refinement of crash avoidance technologies that have demonstrated measurable benefits today. Many of the driver-related errors that lead to crashes today could be ameliorated by the crash avoidance systems if they are more widely deployed and used in production vehicles. Mark, you and I just spoke about this. But this also has implications for AVs. Let's examine the fatal pedestrian crash with the Uber AV test vehicle in 2018 to see why crash avoidance technologies will continue to be important even with AVs. There are several factors that made such a crash practically inevitable. First, the driver assistance and crash avoidance systems on the host Volvo XC90 were disabled when the Uber's automated vehicle driving system was in control. The Uber system's emergency braking maneuvers were also disabled to reduce erratic vehicle behavior. Uber was conducting nighttime testing with inadequate headlights. The XC90 was rated poor in our headlamp testing by IIHS. The testing protocol involved a single safety driver responsible for monitoring both system information through the vehicle center stack, as well as the safe operation of the Uber system in the road environment. Now, remember, this is an issue because as we just discussed, humans can struggle to supervise vehicle systems and the road for extended periods without physical involvement in the driving task. And lastly, the safety driver apparently ignored the prohibition against internal distractions as she was watching a video on her phone right before the crash. And this video shows the forward road-facing view taken from the vehicle, the Uber test vehicle at the moment of the crash. You can see from this screenshot of the video that the pedestrian was not visible until just before the crash due to the Volvo's poor headlamps. Here is what the road scene looks like under daylight conditions. And here is an aerial view of the scene of the crash. You can see that the pedestrian path does exit to the roadway despite not having a designated crosswalk. And unfortunately, the Uber test vehicle's AI was not trained to anticipate pedestrians crossing the road, except at designated crosswalks and intersections. So this schematic shows the path of the vehicle relative to when the pedestrian was in view of the Volvo's rated poor headlamps. Remember, the Uber test vehicle had Volvo's forward crash avoidance system disabled. If that crash avoidance system had been turned on, the crash very likely could have been avoided. Now, crash avoidance technologies offer safety benefits that can be observed today, whereas the safety benefits of autonomous vehicle technologies are only hypothetical right now and rest on a variety of assumptions about the robustness and safety of their designs. While the industry's focus right now is on the push to develop more sophisticated forms of driving automation, there should also be a continued effort for the development and refinement of current technologies that have been shown to reduce crashes and crash severity. But the thing is, as I've mentioned multiple times in this session, these systems need to become more widely available in consumer vehicles and also to be more widely used by consumers in order to maximize their safety potential. And so that brings me to the end of my talk. So I guess we can do another round of Q&A. Mark, you're on mute.
Thank you. How many times have we heard that over the last 7 months or so?
Every time I join a video conference, every time.
And I pride myself on not being muted, but you caught me that time. Look, thank you. That was terrific and very thought-provoking because there are there's certainly lots of perceptions around this, and it's useful to have some useful facts to mix with a lot of perceptions and potentially misperceptions as well. Now, I do have a few questions that are from Q&A, and I also encourage those who are listening tonight, to ask a number of questions as well before we close. So there are a few around some of the earlier presentations. Are you happy to take those sort of questions on as
absolutely.
well? That's terrific. And then we'll just come back to the final presentation because I'm intrigued about one or two questions, 2 points that you've mentioned here. So David Shinner, you may know well. I've known David for a long time. He's asking a question here, I think really pertinent ones, which is, firstly, just in relation to the probabilities of crash prevention, what databases are used for probabilities and crash prevention of the different systems? Maybe from the perspective of IIHS, you could probably answer that.
So we use police reported crash data. Obviously the NIMVIX can be very useful for the analysis we did with the AV study, but as that study was run between 2005 and 2007, many of those vehicles did not have crash avoidance systems that we've been talking about today. So other databases, for example, from NHTSA, are updated on a yearly basis with vehicle information. We also have insurance claim data that our sister organization, HILDI, is able to analyze and show reductions in claim rates, for example, to show support the efficacy of these crash avoidance systems. I mean, if David would like to email me directly, I can get a list of specific databases that we've used in the past for various analyses.
Great. I'm sure you'll be able to. The email.
Yeah, my email's right up there. So
that's
just send me an email and I'll.
Yeah. I mean, David did ask, the next question was just about crash severities. Because of the auto brake, as you call it, or autonomous emergency braking, clearly has considerable benefit, particularly also with low sort of injury type events, the rear end and the like. So any comment on data around looking at the systems and their efficacy in relation to crash severity and then consequent injury severity?
Yeah, so I mean, with our testing program, we rate these vehicles basically not just whether they come to a full stop, but also the degree to which they slowed the vehicle before hitting targets, because obviously speed reduction is directly related to crash severity. And as for crash severity, unfortunately, cannot be captured in insurance data. Insurance claim data are very wide, but not very deep in terms of the degree of detail about the claims themselves, and even if they're collision claims. So I can't really speak right now to the crash severities per se, but we do know that there is generally a net benefit of these systems. And even though, for example, the harsh braking that we talked about can actually have some unintended consequences of being rear-ended yourself when your vehicle abruptly brakes and the person behind you doesn't have auto brake and, hits your vehicle. That has been demonstrated. Jessica Cicchino did publish a study on that. But the point is the net benefit of having these systems vastly outweighs being the possible negative effects of those systems, and hence why we're encouraging a net proliferation of these systems.
Great. Another question here from Nawid, who asks, what would be the primary requirements and policies prior to launch of autonomous vehicles? Please answer in relation to scenarios for both a sort of high income and low and middle income countries. So what would be the primary?
Sorry, Mark, can you repeat that one again for me, please?
So what would be the primary requirements and policies prior to launching autonomous vehicles? So It's a big question, that one. And in
That's a
terms
big
of,
question, and one we
yeah,
haven't figured out. That's the
no,
whole
exactly. And
problem.
capturing
So,
it, and
yeah,
it varies in high income as well as low and middle income countries. Look, I think that's you could spend a long time talking through that, right?
yeah. It's a good question,
Yeah.
and it's a question that, I mean, different organizations, different governments are really struggling to handle. And the problem is the regulations need to consider a huge span of factors, ranging from the individual consumers to the infrastructure to the testing verification process, data availability, fleet maintenance and management. I mean,
Yeah.
huge range of
And
factors.
then there's all the legal ramifications as
Or
well, and insurance
insurance of
elements.
AVs.
So there's further questions that Noah's asking as well around network screening. So you've sort of touched on that. Look, I know here in Australia, we have government agencies who spend, just working tirelessly on so many of these questions in preparation for it. So one would hope that much of what is being developed in many of the high income countries will have enormous utility in low and middle income countries. I mean, more so in those countries, obviously, who are rapidly motorizing with traditional motor vehicles rather than motorcycles. But I think there's a lot of potential for to be able to utilize much of the work that's being done now.
Yeah, there is.
In other countries.
Sorry, what was that last bit?
Do you think there's that potential for transference of some of those, some of the extensive work being done in North America and elsewhere to prepare for the advent of autonomous vehicles that could have enormous utility in low and middle income countries?
So on the surface, I want to say yes, but with a huge but. That being, we were talking about, for example, two-wheeled motorized vehicles being most common. And of course, those vehicles tend to be the most erratic and the least predictable. Also, detecting them is also a problem as well for a lot of camera-based systems. And one problem, so the reason again why our analysis did not look at a mixed fleet scenario is a mixed fleet scenario is going to have so many unforeseen consequences of introducing AVs into the fleet that we can only begin to anticipate based on the vehicle testing situations that we're seeing now with prototype systems. I mentioned before Eric Teo and David Kidd's study. They found that actually human drivers were the ones crashing into the vehicle, the test vehicles. Right. And so this introduces a whole range of issues that we're not considering. Like, for example, how are AVs going to communicate to non-motorized or non-autonomous unconnected vehicles? How are they going to, not just the communication, but also how are they going to predict, anticipate behavior? Because we found, for example, in our analysis, incorrect, like false assumptions about the actions of other vehicles and what they're going to do next was a huge contributing factor to the crashes that we've seen. If human beings we're very good at adopting social norms in terms of local driving behavior and acceptable like subtle nuances. That all has to be programmed into AVs, and a lot of it we're not even aware that we're doing it. So, AVs are not human, and it's very likely that AVs will be developed in a way that, yes, they'll be developed by human programmers based on idealized human behavior, but they're still not humans. They still have completely different protocols and behavior criteria that human beings may not have. So it's very likely they may not drive like a human. Especially in a mixed fleet scenario, that could have all sorts of ramifications for human AV interactions.
Look, I imagine as the audience have many questions I'd like to ask you. I mean, we haven't even begun to talk through the connected ITS in relation to vehicle to vehicle and vehicle to infrastructure and the promises particularly emanating from the US DOT 10 years ago, just about how effective that would be in terms of crash mitigation. So look, we could talk for hours, and look, it's just been an absolute delight to be able to chat with you about what we're seeing in relation to the transition from level 0 to right through to level 5 today and tonight. I would just like to thank you for making the time to share, the jewels that you have in relation to this, and encourage all of those who are listening tonight to reach out to you and to the Insurance Institute, who've always been doing tremendous work in this area to assist us in that path towards automation. And thank the organisers, the university in Cali and Columbia, and particularly IIHS, and encourage those who are not familiar with IIHS to take a look at our website and participate in some of the activities that we have across the year. So again, thank you, Alex. It's been just a delight and pleasure to chair this session.
Thank you for having me.